So today our topic is electric potential and potential difference. So electric potential means that suppose we want to, let's say we have a point charge, source charge, positive charge placed at some point, fine, and here it's at O, let us say some charge is located plus Q, and there are say 2 points, fine, say point A and point, let's say B. We need to bring test charge which is placed at point A to here. Some work need to be done, and the work which is required to move this test charge Q naught from point A to point D, right, in the electric field of this charge plus Q is called the potential. So potential is it is denoted by V. Potential is V. V is equal to work done, that is W upon test charge Q. This is the amount of work done in moving the test charge from infinity or from any given point which is beyond that, from towards the source charge Q in the electric field of Q. That is called the potential. So, or we may say the potential at point A, we say VA, and potential at B, say VB. So potential difference will be equal to VB minus VA. This is again equal to work done upon charge Q naught. So potential difference between any 2 points can be defined as the amount of work done in moving a unit charge from the one point to the other point against the electrostatic forces, right? Against the electrostatic forces in the electric field of this. So units of potential will be volt. This is 1 volt is equal to 1 joule or 1 coulomb, or we may say 1 volt is equal to joule per coulomb. Joule per coulomb is the unit, right? So we can say that potential difference between any 2 points is it is 1 volt. It's said to be 1 volt if 1 joule of work is done in moving a positive charge of 1 coulomb from one point to other against the electrostatic forces. Right. Now let's find out its formula. How are we going to calculate it? Fine. So let's say calculate electric potential due to point charge. Let's say here is the charge at point C, O, fine, and we need to find electric field at point T, which is lying at a distance of let's say R from point charge Q, right? And at point A, say test charge Q is located. We need to move test charge from point A to point T, or say to point, this charge moves from A to point B in this direction against the electrostatic forces, right? So let's say this is the distance moved by this dx, and this point A lies at a distance of say x. Right? Now, the force we need to find move this test charge from A at distance x from point O. Fine. Now, electrostatic force acting on test charge Q will be, this force is due to this charge, source charge Q. So this force is equal to, we know, 1 by 4 pi epsilon naught Q naught upon, this is at a distance of x squared. This is x squared. Fine. This charge moves a small distance dx, and small amount of work is done, say, to move it from A to, say, B. This distance is, say, dx. So this work done will be f dx. Since this is moving against the electrostatic force, right? So there we'll put sign of minus, which denotes that its direction is opposite to the forces acting on it. And total work which is required to move this charge Q naught from infinity to that point P, that is given by integrating this from infinity to point P, which is located at distance say R, right? Which is located at distance say R. Now, what is the value of F? We have, this is work done, negative of infinity to R. F is 1 by 4 pi epsilon naught Q naught by x squared dx. So Q and Q naught are constant. 1 by 4 pi epsilon naught is again constant. We'll take it out. So W is equal to, so minus 1 upon 4 pi epsilon naught Q naught, right? So we're left with dx by, or 1 by x squared into dx. Fine. From infinity to say R. So integration of this will be, so work done is equal to, this is equal to minus 1 by 4 pi epsilon naught. So let it be Q naught. So integration of this will be x raised to power minus 2. I can write over here also. X raised to power minus 2 dx. So this is minus 2 plus 1 upon x minus 2 plus 1 or minus 1 from infinity to say R. So we get W is equal to minus Q naught by 4 pi epsilon naught. So this is x raised to minus 1 upon minus 1 from infinity to R. Right? Now W will be equal to minus Q naught by 4 pi epsilon naught 1 by x, here this is minus R by infinity. This minus and this minus makes plus. So in the next step, putting the value upper limit minus lower limit, we get W is equal to Q naught by 4 pi epsilon naught. Upper limit is 1 by R minus 1 by infinity. So here we get W is equal to Q naught by 4 pi epsilon naught R. So this is the, or we may say 1 by 4 pi epsilon naught into Q naught by R. Now this is the work done. We were finding the potential. this potential is equal to work done upon test charge. We get 1 by 4 pi epsilon naught q naught upon r into 1 by q naught. This goes with this. So we have potential as equal to 1 by 4 pi epsilon naught. This is q by r. This is the formula to find the potential, or this is the amount of work done in moving a test charge from the infinity to the given point against the electrostatic forces. And here we can see that this potential is inversely proportional to the value of R. It's inversely proportional to R. And in case of electric field, the electric field formula is KQ by R square. So that is inversely related to the square of the R. Now we'll find some more derivations of electric potential due to dipole. Now we need to find electric potential at an axial point. Say at an axial point of a dipole. So let's say we have a dipole over here. Right, so this is minus q, this is plus q, and let this distance be say 2a. Right, the distance between them is 2a, and this is the point, midpoint of this dipole, say O, and we need to find the electric potential at point, say P, lying on the axis of here. So let this point P be lying at a distance of say R from this. Right. Now, the first will and total potential will be, that is V is going to be V1 plus V2. The V1 is the potential due to negative charge placed at point A, and V2 is the potential at point B due to positive charge. So V1 is due to negative charge. So this is equal to, let's say write down values of V1. I'll write here only. Oh, okay. V1 is equal to say 1 by 4 pi epsilon naught into, this is due to negative charge, say minus q. So this distance is R plus A. This distance is R plus this R plus this A, because the length of this dipole is 2a. So this part is only A, this part is also A. This is A, this is A, right? Or minus q by, this is A, R plus A. And V2 is 1 by 4 pi epsilon naught into positive charge Q upon, this is lying here, R minus A is the distance, R minus A. The total potential will be V1 plus V2. So 1 by minus 1 by 4 pi epsilon naught Q plus 1 by 4 pi epsilon naught Q upon R minus A. Here it is R plus A. Now, if I take Q common, I am having Q common, 1 by 4 pi epsilon naught common. We are left with 1 upon R minus A minus 1 upon R plus A. Now solving it algebraically, we have Q 4 pi epsilon naught, taking LCM, this will give me R square minus A square. So this is R plus A minus R minus A. But just a moment. Sorry, actually that was very important. So this is R plus A, R minus A. This R goes with this. And we have Q by 4 pi epsilon naught. This R goes with this R and plus A. It gives us 2A. So into 2A upon R square minus A square. So this 2AQ can be written as P. P is dipole moment, we know that, right? So we are left with 1 upon 4 pi epsilon naught. And let's say R is much greater than A. This R is much greater than this A. So we can easily neglect this term A square. So we will be having P upon R square. Right? So this is the formula for electric potential due to dipole. Right? Now let's change this position from an axial point. This is the electric potential due to dipole at a point which lies on the axis of the dipole. Now we'll find the electric potential at an equatorial point of a dipole. At an equatorial point. Of a dipole. Let's see. So here is a dipole. So we need to find a point P which lies on the perpendicular bisector of this. So here it lies P. So this is P, say A. Here it is minus Q. It is plus Q. This is say B. This is perpendicular bisector, midpoint O. So this is A, this is also A because the total length is 2A. Fine. Now, let this point P lie at a distance of say R from the dipole. Now, using Pythagoras theorem, this distance AP, this is equal to say R square plus A square. Similarly, PB is also R square plus A square. Now, total potential will be equal to, total potential due to dipole will be equal to the potential of the two charges, which is V1 plus V2, sum of the potential of the two charges. So V1 is due to minus Q, so this is equal to, let's say write K minus Q by this distance is say 80 plus K into Q upon this distance is say BP, and we have found AP and BP, they both are equal to each other. So AP is equal to BP, which is equal to root of R square plus A square. Using Pythagoras theorem, we have found here. Let's substitute the values. So V is equal to K, or let's take K common out of it and Q out of it. So I can write Q upon 4 pi epsilon naught. So this is minus 1 upon AP. AP is root of R square plus A square plus 1 upon root of R square plus A square. So these are positive and negative, which makes 0. So hence potential is equal to 0. Right? That means the electric potential at a point due to dipole is 0. Equatorial point. Now, this point we will consider this point lying at anywhere outside the dipole. Fine. So we'll say, let's find the electric potential at any general point due to this type. Any general. Or let's say here we draw a dipole. Dipole is made. Right, so this is say minus Q charge, this is plus Q charge. Right. Dipole minus Q plus Q. And here lies the point, say P. So join this, say this is A, this is B. If I join AP and here I join BP, and this is say O. Right? Now, this is the figure. Now, what we'll do, we'll draw a perpendicular from B to this OP and extend this line till here. And we'll draw another point, say, let's say this is D, fine, this is D. So D, and let this point we say C, A perpendicular, we have drawn this. So this OP is equal to say R, and AP is R1 and R2. Or we may say, let's find this is say A, this is also A, this is theta, and by geometry you can find this OD. First of all, AP is equal to this OP plus OD. OP plus OD. Now, what is OD? In this triangle, if this is theta, so using trigonometry, we can get OD to be A cos theta. A cos theta. The length of OD is A cos theta. So OP is equal to say, OP is here, OP is equal to R. So AP becomes R plus A cos theta. Right? And similarly, this BP is equal to OP minus this OC. Now, in this triangle, OC will be equal to this is theta. So, using trigonometry, we have OC be A cos theta. This is R minus A cos theta. Right? So, this is AB and B. Now, let's find the potentials. So, V will be equal to V1 plus V2. V1 plus V2. So, V1 is what? Due to minus charge, this is say 1 upon 4 pi epsilon naught, say minus Q upon say AP, right? Plus 1 upon 4 pi epsilon naught. This is plus Q upon BP. Right? Now we'll substitute the values. Fine. The value will be V is equal to, let's take Q common upon 4 pi epsilon naught. I write so Q by Vp and 1 upon Vp is R minus A cos theta plus first question minus 1 upon this is R plus A cos theta. Now let's solve it. We have V is equal to Q upon 1 by 4 pi epsilon naught. So this will be R square minus A square cos square theta. We have R plus A cos theta minus R minus A cos theta. When we open the bracket, it will be V is equal to Q upon 4 pi epsilon naught. R goes with R. We are left with 2A cos theta upon R square minus A square cos square theta. Right? So R is much greater than A over here. This R is much greater than A. We can neglect A as well as this factor can also be neglected. So we are left with V is equal to 2A write as 2AQ, arranging it cos theta upon 4 pi epsilon naught. Here we are left with R square. Now let's replace 2AQ by P, which is dipole moment. We have V is equal to P cos theta 1 by 4 pi epsilon naught upon R square. Right? So, and if we write the vector form will be V is equal to P, right? P then vector R upon 4 pi epsilon naught R cube. Right? Yes. So we have seen that when P lies on the axial line of this dipole, that means when theta is equal to either 0 or it is 180 degrees, then value of V is plus minus depending upon if theta is 0, then it is 1 by 4 pi naught, 4 pi epsilon naught, Q by R square, and if it is the angle is 180 degrees, it is minus 1 by 4 pi epsilon naught P by R square. Or potential has the highest value, highest positive value, or in the negative side, greatest negative value also. And one point P lies on the equatorial line of the dipole, where theta is 90 degrees. Then potential is 0. Now, we'll move ahead. Okay. Our next topic is, so what is the relation between the electric field and the potential? That's really very important, right? As we, in my first lecture also, when I explained about the units of the electric potential, I said it's joule per coulomb or it's volt per meter, right? So how? Why volt per meter? That I told you earlier, we will discuss it later. So today I'll tell you what the relation between the electric field and the electric potential. Fine. Suppose relation between electric field and electric potential. Fine. Let us consider electric field of a point of a source charge, say Q. So here it lies the plus Q charge. We need to find its potential. So this is a positive charge. So its electric field will be in this direction, right? So यहाँ पे point A ले लेते हैं. Let's take point A, and here it is say point B. Fine. So test charge we placed at say point Q naught. So let this move this, or we may say the potential at point V, point A B, say V. At potential at B, we say V plus D V. Little more than that. It's little more than that. Fine. So V and V plus DV. They are the potential at point A and point B. Now the electric force which is required to move this test charge against the electric field. So electric field is in this direction. Against the electric field, right? The force required to move this test charge against the electric field, right? Say towards the source charge. This is equal to force. It will be negative sign. Q naught E. E is the electric field. Q naught is the test charge. Because it is moving, we are moving it against that electric field of the source charge. That's why we have taken negative sign. And work done will be equal to force into distance. That is equal to dr. This is the distance, say dr. As we moved, right? So this distance is dr. It will be equal to minus Q naught E into dr. Right? And we know the work done in moving test charge from A to B is also given by this work done is equal with, from the definition of potential, we have work done on charge, right? So this work done is equal to charge into the potential difference, VA minus VB. So this work done is equal to charge into potential difference. That is Q naught into. So this VA minus VB, right? That is the potential difference, or VB minus VA. Right here, VB is greater than VA, so this is VA. So VB is V plus VB, and VA is V. So we have Q naught into, we are left with D. Q D P. Equating these two, we get minus Q naught EVR equals to Q naught dV. So this Q naught gets cancelled, right? And we have electric field as minus dV by dr. This is called potential gradient. This one. This is called potential gradient, because here the potential is considered with respect to the distance. So any quantity, when we take it into consideration with with reference to the distance, that becomes its gradient. So this is the potential gradient. So our negative of potential gradient is the electric field. So E is minus dV by dr. That means this is the rate of change of potential with the distance and potential gradient, or electric field is always equal to electric field, we say at any point is always equal to the negative of the potential gradient at that point, right? So units will be volt per meter. Fine. So 1 volt per meter is also equal to Newton per Coulomb. Volt per meter is equal to Newton per meter. How? Because this question is normally asked in the MCQs or in the 1 markers. Fine. So what is this volt? Volt is work done on charge. So this is joule per coulomb upon dr is nothing, it's a distance only. So right, it is meter. It is meter. So joule is work done. Work done means Newton into work done into force into distance, that is Newton into meter per coulomb. Meter, this meter goes with this becomes Newton per coulomb. Newton per coulomb. And this is volt per meter. Volt per meter is also written as Newton per coulomb. So these two are the same. These two units are the same for this. They represent the same physical quantity, which is electric potential. Just a minute, please. Now, so what are equipotential surfaces? So any surface that has same electric potential at every point on it, it's called the equipotential surface. The surface may be surface of a body or any surface in space, but potential must be same. So no work is done in moving a test charge over an equipotential surface, right? So then, second is, if the electric field is always normal to the equipotential surface at every point. Because if the field were not normal to equipotential surface, then what would happen? It would have a non-zero component along the surface. So to move a test charge against this component, some work has to be done. So since there is no potential difference between any 2 points on an equipotential surface, so no work is required to move a test charge on surface. So hence electric field must be normal to the equipotential surface at any point. Right? And equipotential surface, they are closer together in a regions of strong field, and they are farther apart in the regions of the weak field. As we can see, that electric field is minus dV by dr. Fine. And we can write dr as dV by E, or for the same change in value of the dV potential, we'll say dV is going to remains constant. So dr is inversely related to the electric field. And no two electric potential surfaces, no two equipotential surfaces can intersect each other. If they intersect, then there will be two values of electric potential at that point of intersection, which is not possible. Which is not possible. Right? Okay. Fine. Now, let's come to the potential energy of the electric field now. So this is just hold this. So now we are going to find the potential energy of a dipole in a uniform electric field. potential energy of a dipole placed in a uniform electric field. Electric field, right? So let's go into the parallel line of the electric field, which indicates that the electric field is uniform everywhere, and here is the dipole. Right. So this is -2 plus 2, right? And electric forces will be equal and opposite. So at this point, force will be two times E, and in this direction, it will be Q times -2 times E. And it's the length between these two is so length 2, and let this be the theta with the angle between the electric field and the dipole. Now, these two forces are equal and opposite, so they make translative force at 0. But here, if couple is formed, so it has to rotate. So when the rotational force is, we know that is low. So to rotate it, a torque is produced. The torque is what? Torque is the force into perpendicular distance. So this is force into perpendicular distance. So perpendicular distance is what? That's 2a sin theta. This is theta. So this is 2a sin theta. So this force is, let's say, QE into 2a sin theta. Again, 2aq is nothing but dipole, right? You can write it as a dipole. 2aq is P, fine. So it will be written as 2aq into P sin theta. That is P E sin theta. Right? P sin theta. Fine. And work done will be how much? So we need to find the work done. So this angle, let this dipole rotates to a very small angle, say d theta. The small amount of work is done on it. Fine. So that work done will be equal to, say, dw. Right? So that is very small amount of work done. So dw, this work is done due to torque into d theta. Torque into d theta. The value of torque is Pe sin theta. So dw is equal to Pe sin theta into d theta. Right? But we need to find the total work done. So total work done can be found by integrating this. So that is dw, integration of dw, right? From, say, any two angles, let the first initial value be theta 1 and the final value be, say, theta 2. So theta 1 to theta 2. This is Pe sin theta into d theta. Right? Now, so integration of, so this is w is equal to integration of sin theta is minus cos theta. So P is constant, P will be written here. So this is minus cos theta. Minus cos theta from theta 1 to theta 2. Right? Now, so we have Pe minus cos theta from theta 1 to theta 2. Now putting the upper value and lower value. Right? That is W is equal to Pe minus cos theta 2 minus of minus cos theta 1. So that becomes positive, or W equals to Pe cos theta 1 minus cos theta 2. So this is the work done right? And this work done will be stored in it as its potential energy of the dipole, and we can denote this work done W by right. U is the potential energy. U is denotes the potential energy. So we can write U in place of W. So U will be equal to PE cos theta 1 minus cos theta 2. Right. Now, depending upon the value of the theta, say if initially the dipole is oriented perpendicular, that means if say theta 1 is 90 degrees and it's brought to same orientation, making an angle say theta with the field. So theta 2 is say theta, right? So we can have theta 1 is 90, theta 2 is theta. What do we get? Cos 90 will be 0 minus cos theta. Fine. So we have u, when we have say theta 1 equals to 90 and theta 2 equals to theta, we have u is equal to PE cos theta 190, so it will be 0 minus theta. So this is minus cos theta, or whole is equal to, we can say, minus PE cos theta. You can write it like this, minus PE cos theta. Fine. Now, this is the formula for the potential energy. But depending upon the theta, its value may vary. Let's say if theta is equal to 0. If theta is 0, so cos 0 is 1. So value of potential energy will be minus PE. So minus PE, that means it has the minimum value. So the potential energy of any dipole is minimum when its dipole moment is parallel to the external field. Then when theta is 90 degrees, potential energy will be 0. That means when a dipole is held perpendicular to the external field, its potential energy will be 0. And when say theta is 180 degrees, if theta is 180 degrees, cos theta is minus 1. So this value comes out to be U will be equal to plus PE. Right? So that means if the value of potential energy will be maximum when dipole is anti-parallel to the external field. Right? So I think that's all for today. We will continue with the capacitors. Next topic will be capacitors. We'll continue in our next class.